Thanks, Kyle. Good morning, everyone. So yeah, I'm excited to present some recent results that we've been getting at DeepMind on using deep learning for mixed integer programming. Before I start, so we have an archive paper which has a lot more details than what I'm presenting today. So I'll just be presenting a very high-level, short summary of the work, but please do look at the paper for more details. And this work was done with several collaborators who are listed here, both at DeepMind as well as Google Research. All right, so let me jump in and quickly give a short background on mixed integer programming, or MIP. So integer programming is the problem of optimizing a linear objective function over a set of integer variables with a set of linear constraints. And so as you can see here, the linear objective function is C transpose X, and the constraints have the form AX less than or equal to B, where A is a matrix and B is a vector. And what makes the problem hard is, of course, the integrality constraints. If we were to ignore them and consider the continuous relaxation, we get what's called a linear program, which is solvable in polynomial time. But with the integrality constraints, we get an NP-complete problem. And the mixed integer programming refers to the fact that you can have both integers and continuous variables in X. And as most of you would know, this has a lot of real-world applications. In some sense, mixed integer programming is a very powerful language for expressing optimization problems that makes a very good trade-off between expressiveness and tractability of search. So the linearity of the objectives and the constraints make the search very tractable. And it turns out that many real-world problems can be expressed in terms of linear objectives and linear constraints. So just the breadth of applications in itself acts as a huge motivation to see whether we can improve solvers for this problem using deep learning. And of course, there are many commercial and non-commercial solvers already available for this problem. And the question is, can learning add anything beyond what these solvers already currently achieve, which is already extremely impressive. Okay, so why learning, or how can learning possibly help in this domain? The idea here is that in a real-world use case, instances would come from some very narrow distribution. And if it is possible to sort of automatically adapt your solver to that particular distribution in exchange for better performance, that is a useful capability to have, right? So state-of-the-art commercial solvers, they need to be sort of designed for all kinds of use cases because it's sort of hard to adapt them to a particular use case by the end user. Whereas what learning provides is a way to adapt to a specific application that the user cares about, right? And the idea is, that corresponds to a particular distribution over the MIP instance space. And if we can draw samples from this distribution and train an optimizer on those samples, then on subsequent samples that we would draw from the same distribution, that optimizer could potentially do a lot better than a solver that's agnostic to that distribution. And this fits how MIP solvers are actually used in the real world, because typical applications require solving many instances that are highly related to each other. So for example, one of the applications that I'll show results for is this packing problem that we solve in production at Google, which actually gets solved about 6,000 times every month. Now, no two of those instances are identical, but they're all highly related because the underlying semantics doesn't change much. But the specific parameters, the C vector and the objective function and the A matrix and the B vector and the constraints, they keep changing from instance to instance, but in a very structured way. So if you could learn on past instances, you can hope to do a lot better on future instances. So that's the motivation for applying learning into this domain. Now, this already has a huge amount of work in the literature, and you know, it would take way too much time to cover all of them. I've just listed a whole bunch of references here, but you know, just MIPS alone have been considered in many previous works, including works done by many of the attendees of the workshop. And you know, that includes learning primal heuristics, branching policies, cutting policies, and configuring MIP solvers and so forth. So we are sort of building on a rich existing literature. Okay, so before I go into the details of our approach, I just want to quickly explain a few basics about how a MIP solver works. So as I mentioned before, the input parameters are the A matrix and the B vector that define the constraints, and then the C vector that defines the objective function. So given those three quantities as input, a MIP solver does a search over the X space in order to produce two different outputs. One is to generate an assignment for all the variables in the problem. And the other is to prove a lower bound. So let's assume we're dealing with minimization. The second output of a MIP solver is to prove a lower bound, so that by looking at the objective value of the assignment produced by the solver and this lower bound, it becomes possible to say how far from optimality is the assignment generated by the solver. Now, that proof is generated typically using tree search, and then by looking at, so the tree search is over assignments of the integer variables, and then by looking at sort of the linear program objective values across all the leaf nodes, it is possible to say that to prove a lower bound. And then that allows us to evaluate how close to the global optimum the assignment is. Our approach basically applies learning to both of those two subtasks of producing an assignment as well as proving the lower bound. So I'll go through each of those two parts one after the other. So the first part, which generates an assignment, we call it neural diving. And it's basically a generative model that conditions on the specific MIP instance that we want to solve. So basically the A, B, and C parameters of the MIP. And in turn, it defines a distribution over the assignment space, over the variable space that we are searching to generate an assignment. Then what we do is we draw samples from that distribution represented by a neural network. And instead of drawing complete assignments, what we do is we define partial assignments. So we might only assign, let's say, 80% of the variables and leave the rest unassigned. And since we can sample as many times as we want, we typically would sample k samples from this model. And then the unassigned variables would end up defining a much smaller MIP than the original MIP that we wanted to solve. And what we do is, so we call that the submip. We then solve that submip using an off-the-shelf solver in order to complete the assignments. And then given such k complete assignments, we then pick the best and we report that as the output of the neural diving component. Then the second component, which then proves a lower bound, we call that neural branching. And as I mentioned before, this involves tree search. And the way we apply learning to this tree search is by learning a branching policy that says, given the current search tree, pick a leaf node, and then at that leaf node, decide which variable to branch on next in order to expand the search tree. So the choice of the variable is made by a neural network such that it can prove the lower bound in as few steps as possible. Okay, so those are the two main components. of our work, and then we put them together into what we call a neural MIP solver. And the hope is that the neural MIP solver is better than a state-of-the-art solver. Now, I want to emphasize that this is a hybrid approach. So in particular, in neural diving, when we solve the submip, we use an existing MIP solver in order to solve the submip. And then when we do neural branching, we're actually running the tree search inside an existing solver so that we can make use of many of the existing heuristics that the optimization community has developed over several decades of research. But then, we enhance it by using a learned branching policy. And the way we represent a MIP as an input to a neural network is basically by representing it as a bipartite graph, where one set of nodes in the graph would correspond to the variables that we are optimizing over, and the other set of nodes would correspond to the constraints and the objective function. And the edges would indicate whether a variable belongs to a constraint or not. So this is a fairly standard representation that has been used in many of the previous works for the past several years, and we're basically using that same representation here as well. So the nice property of this representation is that it's permutation invariant. We can shuffle the variables and put it through a graph neural network, and it'll still produce the same output. And it can also handle variable-sized instances. So in typical applications, you will not have fixed size instances. You will have changes in the sizes from instance to instance. And this approach of representing it as a graph and then applying a graph net on it can handle variable sizes. All right, so let me explain each of the two components in turn now. Again, it's going to be fairly high level. I ask you to look at the paper for more details. As I mentioned before, the aim is to learn a conditional distribution, condition on the MIP to be solved, define a distribution over the variable space. And in particular, we restrict this distribution to only the integer variables. And we use a simple energy-based approach here where we treat the objective function as an energy, assuming we're minimizing here. And then we learn the parameters of this model to represent that distribution as well as possible. And by using this sort of generative modeling approach, we can now draw multiple samples, and that naturally lends itself to parallelization, which I alluded to earlier. Okay, and the way we would train this model is by collecting a data set of MIPS, and then we would use an off-the-shelf MIP solver and run that solver on those instances for very long time limits. For example, we typically run it for 24 hours, and then collect all the intermediate solutions that the solver found on those instances and use them as training data for fitting the parameters of the model. So this again is a graph neural network. I won't go into too many details. We've applied several different ideas here, conditionally independent models and autoregressive models and so forth. The best results that we have gotten so far is for a conditionally independent model that predicts values for each variable conditionally independently given the input MIP. Okay, so now let me go into the second component, neural branching. So here, there's a very natural way to formulate this problem as a sequential decision process, whereby an agent is basically selecting a variable to branch on at each step of tree search. And the environment basically maintains the state of the search tree. And given an agent's action, it would carry out that branching action on the current search tree, and then it would send a summary of that updated search tree back to the agent, and again the process repeats. And the reward here is how much closer did each action take you to proving the optimality gap that we desire. So as I mentioned before, the environment here is basically built using skip. So we rely on skip's tree search in order to carry this out. But instead of using one of the existing heuristics in Skip for making branching decisions, we use a neural network to make those decisions. And Skip is, I should have explained, is the state-of-the-art non-commercial solver for solving MIPS. All right. So here we treat, so as I mentioned, it's a sequential decision process, but here we rely on imitation learning in order to learn the policy. So it turns out, and this is something that many previous works have already exploited, there is a classical policy from the optimization literature for making branching decisions called full strong branching, which has been empirically shown to produce very small search trees for proving the lower bound, but it is extremely expensive, so it is not actually used in practice. But this is fine as a target for imitation learning because we generate data offline. So the expensiveness of that policy does not hurt us at test time. And then, given trajectories of this expert policy, we train a neural network to imitate that policy. And since the neural network is orders of magnitude faster than the expert that it's imitating, at test time, it still allows us to perform well. And here, so we proposed a new version of full strong branching that uses, it's much more scalable than the classical approach by making use of GPUs. So I won't go into the details of this, but the short explanation is full strong branching requires solving a large number of linear programs at each step. And our approach basically batches all those linear programs on a GPU to solve them very efficiently. And that allows us to scale this approach to much larger instances than what's possible with the classical approach. And in terms of imitation learning, we've used fairly off-the-shelf techniques like behavioral cloning and dataset aggregation. Again, for details, please see the paper. In terms of evaluation, so we wanted to show how well these techniques work on real-world data sets, large-scale, realistically scaled data sets from the real world. And these are the different data sets that we have looked at: neural network verification, optimizing electric grid operations, and then we also collected data for 2 production applications in Google. And then we also considered MIPLib, which is this standard benchmark used by the MIP solver community to evaluate solvers. Now, all these data sets except MIPLib, they all correspond to one application. So all these instances are variations of the same underlying semantic problem. In the case of MIPLib, there are actually many different applications combined together. So it's not a single application, but yeah, many different applications put together. So the expectation is that,
I wanted me to give you a 5-minute warning, just.
Sure. The expectation is that learning will help quite a bit on single applications because of the shared structure among instances. And the other thing I want to emphasize is that these instances are actually fairly large. As you can see, a lot of the instances are tens of thousands of variables and constraints and more, some going up to close to millions of variables and constraints. And this is after pre-solving them. So we pre-process them to reduce the number of variables and constraints as much as possible. So these are not the raw instance sizes, but after pre-processing to reduce their sizes. And the scale is much bigger than what has been considered in the literature so far. Okay, so we train separate models on each of the data sets. And then the way we evaluate them is by running them on unseen instances for each of the data sets. So we are testing for generalization. And the metric we use is what's called the primal dual gap. We average that across all the test set instances and plot them as a function of running time. So basically, the primal dual gap evaluates how close the upper and lower bounds, the best known upper and lower bounds, are at any given point in time of the optimization. And we want to reduce that gap as quickly as possible as a function of time. And the baseline we compare against is skip, where we tune the hyperparameters of skip on each of the data sets separately by doing a grid search and evaluating each hyperparameter setting on a validation set. So in some sense, that's sort of the minimal learning we can apply on a classical solver. And yeah, we evaluate how well we perform against that. And then in terms of the neural solvers, now we have different possibilities. We can use both neural diving and neural branching together, or only one of them in isolation, with the other, the task being carried out by skip. Okay, so let me very quickly go over the results. In the paper, we have another data set called Correlate. I've decided to omit it here because it's the smallest scale data set and it's kind of trivial. The surprising, one of the surprising results we got was that on MIPLib, we are actually better than TuneSkip by a significant margin. So, after 10 to the 4 seconds of running time, we get a 1.5 times better gap than TuneSkip, which was completely unexpected given that, they contain many different applications. So we were not expecting learning to pick up on much shared structure across instances. And then on the production problem, so in the production packing problem, again, you can see that, so the curves to compare here are blue and magenta. Those are the learned models against black, which is TuneSkip. And you can see that, blue and magenta end up reducing the gap a lot faster than black TuneSkip, although TuneSkip then eventually catches up. And then on the verification data set, again, we get a huge improvement. Blue is about 4 orders of magnitude better than TuneSkip. On the other two data sets, we are basically comparable, maybe slightly better or the same as TuneSkip. And, yeah. So across all the data sets, we either match TuneSkip or outperform it. The other surprising result we had was we took neural diving and we asked whether we can apply the same approach to a single MIP. So now we no longer have a big training set, but instead just a single instance. And the way we applied learning there is by assigning values to some of the variables to define smaller MIPs out of the original single MIP, train a neural diving model on it, and then after training, apply it back to the original MIP that we are interested in solving. So we then applied this approach to several open MIPs in MIPLib. So these are basically some of the hardest instances in MIPLib for which none of the solvers so far have been able to prove optimality yet. And on 3 of those instances, we managed to get the best known objective value so far, which was, again, completely surprising given that we're just learning on a single instance. All right, so the main takeaway here is that this is sort of the first demonstration that learning can actually work on real world scale and beat a state-of-the-art solver like Skip. It's the state-of-the-art non-commercial solver Skip on those data sets. And the surprising finding that learning can even work on MIPLib was completely unexpected for us. Again, that just shows that learning is quite powerful in this domain. Now we're focusing on improving our learned primal heuristics even better. In particular, we're focusing on this neural large neighborhood search approach that I referenced here as our next step. Thank you.